So the first problem is about the following repeated game. So a gambler bets $1 for every game. So he or she has three possible outcomes. She may get $2 back, meaning that she wins $1 with probability 0.4. And with probability 0.1, she only gets $1 back. And in this case, it is neither win or lose. In the last case is that she gets nothing back, meaning that she will lose $1 with probability 0.5. So if we denote xi as the outcome of the ice game, then according to this distribution, the gambler will win $1, so which is +1 with probability 0.4, and 0 with probability 0.1, and -1 with probability 0.5. So this is the probability mass function for this xi. Use central limit theorem to approximately find the probability of being ahead after playing 100 such games. Okay. Meaning that if we look at S100, which is the accumulative reward or the cumulative total income that we get after playing 100 games. So it's a summation of all the income. The xi denotes the income for playing the ice game. Sum of xi from 1 to 100. Okay. This total sum, we need to find out the probability that this total sum is bigger than 0. Okay. If this is bigger than 0, means that after playing 100 games, we earn something back. And this is equivalent to say, because if we want to play 100 games, we have to bet $100. Right? Each game costs us $1. So which means we need to win more than $100 throughout these 100 games. Okay. So let's look at so this can be done using central limit theorem because all the xi's are IID, independent, identically distributed random variables. And we know by the central limit theorem that the sum of all these random variables is approximately Gaussian. In fact, it's the normalized version, is approximately Gaussian. Yn, which is Sn minus the mean subtract the standard deviation. So the solution is very simple. We know the distribution, the PMF of each xi, right? And in particular, from this PMF, we can calculate this mean and variance. Okay, you can just calculate these statistics. Based on that, we can define this S to be the accumulation of all these x from 1 to 100. Now, based on that, we can know the mean of the S is -10. It's basically this number times 100 gives a -10. The variance is the variance of each individual xi by the variance property, right? This is 100 times the variance of each individual xi. So we get 89. Right? So we have the mean and the variance. And by doing that, we know that, so we are looking at the probability of this S bigger than 0. Okay. And we know by the central limit theorem, the normalized S follow the Gaussian distribution. So we equivalently, consider the normalized event. So S subtract the mean, which is -10, divided by the standard deviation, the square root of the variance. So these two are equivalent, but now after normalization, this entire random variable is approximately a standard Gaussian random variable by the central limit theorem. Therefore, the entire probability can be approximated by the CDF function, the phi function of a standard normal random variable. Okay. So in the end, it's 1 minus phi. And I think this number is related to this threshold. So just view this as a standard Gaussian random variable, and you can calculate this probability using the phi function. So you get about 14% probability. Okay. So problem 2 is very similar. So we have a sequence of random variables xn that models the number of products of a factory on the day n. And on each day, this xn, the productivity is independent identity distributed. So it's IID sequence of random variables with mean 5 and variance 9. So we know the mean and variance of each xn. Okay. We want to find an approximation to the probability that the total number of products produced in the first 100 days is less than 440. Well, basically, the total product in the first 100 days is sum of xi from 1 to 100. And so we can just use central limit theorem to do that, because we know all the statistics, mean and variance of xi. Okay. So following this solution, we can calculate the mean and variance of this total sum. So the mean of this one, because it's IID, so by the linearity of mean, is 100 times the mean of each xi. So it's 5. And variance of this one, the variance of sum of these random variables, because they are independent by the variance formula, is 100 times the variance of each xi, which is 9. It's variance. So we are looking at the probability that S100 is less than 440, right? The total number of products in the first 100 days is less than 440. So we are looking at this one. And this, I think this is a typo. So this is, so we do a normalization. So S100 subtract its mean and divided by the standard deviation. So the mean is 500 given here. Standard deviation is square root of the variance, like it's 30. After a normalization, we know that this is approximately, by the central limit theorem, this is approximately a standard Gaussian random variable. So we can use the CDF function, the phi function of standard Gaussian, to approximately calculate this probability. And the rest of the steps are just numerical calculations. And for part B is the same thing. So we are looking at the total number of production in the first n days is bigger than 200 plus 5 times n. So we are looking at the largest value of n find a largest value of n such that this probability is less than 5%. Well, we can ignore this part first and try to approximate this probability using the central limit theorem. So for this one, right, this sum is basically Sn. So we are looking at the probability of Sn bigger than 200 plus 5m. And we know that we are going to do a normalization. Okay, so subtract the mean divided by the standard deviation. And similarly, for the right-hand side, we need to subtract the mean divided by the standard deviation. So this one is equivalent to this one. But now this guy can be modeled approximated by standard Gaussian distribution. Okay? So we can use this probability can be approximated by the CDF of phi function in this way. And then you get this inequality. And then you check the table for phi function. You can get that in order to get 95% inside this entire argument should be approximately 1.65. So you actually require this number to be bigger than 1.65 in order to get this inequality hold. And from here you get must be smaller than 1632. So this is the biggest number that we can have. And part C is the calculate. So let capital N be the first day on which the total number of gadgets produced exceeds 1,000. Calculate an approximation to the probability that this n is bigger than 220. So we want to look at probability. We want to calculate the probability of n bigger than 220. Now let's understand this probability in the context of this example. N bigger than 220, meaning that the first day on which the total number of products is beyond 1,000. So the first sentence translates to the inequality that Sn is bigger than 1,000. Capital N is the first day where the cumulative production is bigger than 1,000. We are looking at the probability where this capital N must be greater than or equal to 220. Right. So this capital N is at least 220. Now this probability of this event is equivalent to say that the accumulative productivity in the previous n-1 days is less than 1,000. Or to be more specific, this is actually 219. So in the previous 219 days, the total productivity is less than 1,000. If this is the case, then it will take at least 220 days to exceed 1,000 total productivity. Right. So this event is equivalent to this event. So basically, we are looking at the probability of S219 less than 1,000. And this is we are very familiar with this one. So we know how to calculate this one using central limit theorem. right? So the key is to observe that this probability of this event equals to the probability of the total productivity of previous 219 days is less than 1,000. And the rest of the step is just to do a normalization and calculate this probability using the Gaussian CDF. Okay. So problem 3, starting from time 0, buses arrive at the stop according to a Poisson process with rate lambda. Okay, so with this, if you give me a time interval, I can use this. So this process can tell us the distribution of the total number of bus arrivals within that time interval. So the distribution is Poisson distribution with parameter lambda times the interval length. Okay, so this modeling will tell us how many total bus arrivals can happen within a time interval. We can model its distribution, but in this case, there are two different types of buses, blue and yellow. And here's how we model these different colors. We suppose each arrived bus has probability P to be blue and probability 1 minus P to be yellow. Okay. So basically, this is how you think of this process. Based on the Poisson process, you can identify the total number of bus arrivals within a time interval. Okay. And given suppose there are 7 bus arrivals, and for those 7 bus arrivals, each bus arrival has probability P to be blue and 1 minus P to be yellow. Right? So this is a Bernoulli distribution on each bus arrival. Okay, let NT represent the total number of bus arrivals up to time t. N1t represent the total number of blue bus arrivals up to time t. Basically, NT is the total number of bus arrivals up to t. N1t is the total blue bus arrivals up to t. And apparently, the red NT minus N1t is the total yellow bus arrivals, total number of yellow bus arrivals. Okay, we want to find the conditional probability. The probability that up to time t, there are k blue bus arrivals, given that up to time t, in total, there are n bus arrivals. Okay. So given that up to time t, the total number of bus arrivals n. So we observe n bus arrivals. Given this, what is the probability that there are k blue buses among these n buses? Well, this is a very simple distribution because we know that each bus arrival follows a Bernoulli distribution to be either blue or yellow. Okay. So here, given a total of n bus arrivals, we need to identify the probability where k of them are blue. And this is a binomial distribution. So n choose k. Now we have k blue buses, so it's p to the power of k. Right? Each bus arrival has probability p to be blue. And the rest of the buses are yellow. So this is the probability to be yellow, and how many of them is n minus k. So it's a standard binomial distribution. So this probability is simple because the total number of buses is fixed. This is fixed, so it's just a binomial distribution. Now, part B is to find the unconditional probability. So we are just looking at what is the probability that up to time t, k blue buses has arrived. And we're not conditioning on anything. Apparently, we want to solve part B based on part A, because part A we already have this conditional probability. It's about the same event, but we are conditioning on the total number of bus arrivals. So this motivates us to consider total probability law. So this probability can be decomposed by conditioning. I can just follow the solution. So this probability by the total probability law, I can first conditioning on the total number of bus arrivals and multiplied by the probability of total bus arrivals, sum over n from k to infinity. If you look at, this product is basically the probability of the joint event. Right, because this is a conditional probability, we are conditioning on this one times the marginal probability. So this 2 is the probability of this joint event. So we are sum over this joint probability over so we are marginalizing over the other event. Right? So this will give us the probability of this guy. And this n should start from k to infinity because otherwise it doesn't make sense. This is a total number of arrival. It has to be bigger than the total arrival of the blue bus. So basically we are summing up all different. So we are conditioning on different scenarios of total bus arrivals from k to infinity. And conditioning on that, we want to characterize this. We want to characterize the probability of the probability of that there are k blue buses that arrives up to time t. So this is a standard. It has nothing to do with this problem. It's a standard total probability law. The reason we want to do that is because from part A, we know that this conditional probability is easy to compute. Right? It is binomial distribution. Once we conditioning on the total bus arrival, the total of blue bus is simply n choose k, binomial distribution. On the other hand, this marginal probability is also easy to characterize because it is specified by the Poisson process. This is a total number of bus arrival up to time t. So it's given by the Poisson process. Okay. Now we plug in everything. So this guy is a binomial distribution. So it's given as this one, n choose k, p to the power of k, 1 minus p, n to the power of n minus k. And this is a standard Poisson distribution with parameter lambda times t. Because the time interval we are looking at is 0 to t, it's t. So this is a Poisson distribution with parameter lambda times t. And we are looking at nt, capital NT equals to small n. So we plug in small n in this Poisson distribution. Okay. Now, and then we will sum over n from k to infinity. Sum from n from k to infinity. Now, what you do is to there are a lot of terms that are not related to m. So they are constants, you pull them out. But these are those terms that are not related to small m. For the rest of the terms, right, these are related to m. For the rest of the terms, we can do a change of variable, right? Because n starts from k, goes to infinity. So which means here we have n minus k, and here we have n minus k. You can do a change of variable. So which means n minus k starts from 0, goes to infinity. So we replace n minus k by n. And now it starts from n to infinity. Okay. So this is just a change of variable of these two. The rest of terms are the same. But by doing a change of variable, this guy is essentially 1. Because you can see that some of these terms fits into the standard Taylor expansion of an exponential. Is exactly the Taylor expansion of this guy. Okay, so this exponential equals to this sum, the Taylor expansion. So this will cancel with this exponential. They cancel out. So this gives us 1. So what is left is only the coefficient part. It's only the coefficient part. So this is the probability of that we have up to time t, we have k blue buses. If you look at this distribution, it is exactly the Poisson process with parameter lambda p. Right, it's lambda times p, the Poisson process. So everything here is lambda times p times t. Right? So it is like as if the Poisson process is now the parameter of the Poisson process is scaled by p times lambda. This makes sense because intuitively, the blue bars only happens with probability p. Right? So intuitively, the entire Poisson process, this rate, when you combine these two processes together, the resulting process for the blue bars happen to be another Poisson process with parameter p lambda. Okay, so this is part B. Part C is to find, as opposite to part A, is to find this conditional probability. Part A, we are conditioning on NT, but here we are conditioning on the number of blue buses. So this, and we know that part A is easy to compute. So to get part C, we are motivated to use the Bayes rule. Bayes rule handles this kind of translations where you have one of the conditional probabilities easy to compute. If you want to get the other one, consider the Bayes rule. So from Bayes, so this is Bayes rule. The first line is standard Bayes rule. We want to look at this conditional probability, but this is hard to calculate directly. But the opposite conditional probability is easy to compute from part A. So we use Bayes rule. So the numerator is basically the probability of the joint event, okay, divided by the probability of the conditional event, this guy. So this is Bayes rule. But then everything is easy to compute. This is from part A. Okay. This is given by this binomial distribution. And this one, the standard Poisson process with parameter lambda t, right? So it's given by this one. The numerator is given by part B. Part B happens to be another Poisson process with parameter lambda times p. So this is the from part B, this Poisson process. Now you simplify everything. This is what you get. And if you compare, if you understand this distribution carefully, this is exactly the probability of n minus k buses, yellow buses arrives by time t. Why? Because from part B, we know the blue bus. The blue bus is modeled by the Poisson process with p lambda. So following the same logic, you can prove that the yellow bus follows another Poisson process with rate 1 minus p times lambda. Right? That's why we have 1 minus p here and here. And on the other hand, since we are given that there are k blue buses, so in order to have in total n buses, that means we need to have another n minus k yellow buses, right? So that's why here we have n minus k. Basically, this is equivalent to say that, okay, given I observe k blue buses, so the probability that in total I observe n buses is equivalent to say that I observe n minus k yellow buses. So this result can be interpreted as by time t we observe n minus k yellow buses, and this is the probability that for such an observation. Okay, so the last problem is about such a random process xt. So this is how we define xt equals to x0, which is the initial random variable, the random variable of at the beginning, times -1 to the power of nt. Here, x0 is a Bernoulli random variable. Okay, from this sentence, right? At the initial time t equals to 0, xt takes positive -1 equally likely, right? So which means basically saying that x0 is a Bernoulli random variable and standard Bernoulli. And then -1 to the power of nt. Well, this nt is determined by a Poisson lambda process. Nt is an integer. Therefore, if nt, now -1 to the power of an integer, we know it is either 1 or -1. Basically, if nt is even, then xt equals to x0. If nt is odd, it is -x0. Right, so this is such a random process. Depends on a Bernoulli random variable, depends on a Poisson process. Here we assume nt and x0, these two are independent generated. Part A is to sketch a sample path of xt. So I will skip this part. Basically, you can use MATLAB to generate the sample path, right? x0 is modeled by a Bernoulli random variable, right? So at time t, in order to get xt, you randomly sample a Bernoulli random variable, +1, -1 for equally likely. Okay. And then you also get sample another nt from a Poisson lambda process. I think MATLAB has a function on that. You can Google it. Once you sample these two, you can get a number. In the end, this xt is also either +1 or -1, because x0 either positive one or negative one. And this part is also either positive one or negative one. So in the end, xt is also either positive one or negative one. So it will be something look like this, right? So it's either positive one or negative one. Now part B is the technical part. We want to find the autocovariance function and determine if the process xt is white sense stationary or not. So basically, we need to identify this function. And according to the WSS definition, if this function if this function only depends on the increment t minus s, then we call it white sense stationary. Right, so it's R XTS, the autocorrelation function. This function only depends on the increment. Then we call it WSS. Okay. So we just calculate this function and see if it is function of the increment. And this correlation function is related to the autocovariance function. So, but in this case, let's just follow the definition. Everything comes from definition. So the autocovariance function, based on the definition of autocovariance, is xt minus mu xt. This one. We need to first get the mean of arbitrary random variable at an arbitrary time. So mu, looking at mu xt, this is the mean of xt. We just mentioned that xt only takes positive one or negative one values, right? Because here everything is either positive one, negative one. So xt is either positive one or negative one. So this is how we calculate this mean. Right. And here I claim that the probability of xt being 1 is the same as probability of xt being negative 1. Why? Because if you look at this expression, if nt is even, then xt is a Bernoulli random variable, where it takes positive 1, negative 1 equally likely. If nt is odd, it is a negative of the Bernoulli random variable. Still, this guy still takes positive 1 or negative 1 equally likely. Because one, if you flip the sign, because originally this is equal a fair coin. Now, if you flip the sign, still a fair coin, right? So in the end, for xt, the probability of being 1 is the same as being negative 1. So these two probabilities, they are the same. So everything cancels out. You get 0. A zero mean process. Right, so these two means, this is for any t. Right? So basically, kxxts reduces to the autocorrelation. This is basically Rxts. So let's just compute this expectation. That's the precise definition. Again, we are now here we can assume T is bigger than S. The other case is very similar. It's the same. Here we, without loss of generality, we assume this is T bigger than S. And okay. So first of all, we know that xt, again, we have observed that xt only takes +1 or -1 values, right? Because x0 is Bernoulli, and this coefficient is also either +1 or -1. So in the end, xt is only taking these two values. Therefore, so xt is binary, xs is also binary, also taking either -1 or +1, right? So their product is also from this set, either -1 or +1. Therefore, to calculate this expectation, we just need to, right? So there are only two realizations, either 1 times the probability of xt xs equals to 1 plus -1 times the probability of this one equals the product equals to -1. This is the definition of mean. So we just need to work out this event. Let's look at this one. xt times xs. Now xt equals to this guy. I plug this into here. It's x0 -1 to the power of nt. Now xs is x0 -1 to the power of ns. Continue, x0 square -1 to the power of nt plus ns. Because x0 is binary, right? Positive, -1. So this has to be 1, always 1. So this is -1 nt plus ns. Therefore, in order for this one to be, in order for this product to be 1, we basically require this to be even. Even. And for -1, we require nt plus ns. It's odd. Right, again, let's think about this again. We want to calculate this mean autocorrelation. And we observe that this product only takes 2 realizations. So this mean is calculated in this way. So all we have to do is get this probability of this event. Right? Now we need to understand this event first. And it turns out that the product equals to 1, this product equals to 1, if and only if nt plus ns is an even number. But nt and ns are generated from the Poisson process. Right? And the product equals to -1 if and only if it's an odd number. So we just need to calculate the probability for this one. It is equivalent to the probability that nt plus ns is even. These are Poisson process. But for Poisson process, we know that it is easier to model nt minus ns, the increment. Right? We know the Poisson process defines the distribution of this increment. So we need to further translate. This is summation instead of subtraction. We need subtraction. So note that a claim that this is This is even only if this is even. I claim that this one is equivalent to this one. This one is equivalent to this one. Why? So it's a small trick. So NT plus NS, I can generate an increment in this way as increment plus 2NS. This is what we want. This is always an even number, right? Because 2 times an integer is always an even number. Therefore, it does not change the characteristic of this increment. If this is an even number, even minus even, you get an even. If this is the odd number, odd minus even, you get an odd. So these two are always the same, either even or odd. Okay. Now, what we get is that this product equals to 1 if and only if the increment is even. So this guy is equivalent to probability of NT minus NS is even. And this is first one. The second one is minus the probability of the other part, minus probability of NT minus NS is odd. Okay. Now, how do we get this one? We know NT minus NS is this guy is Poisson distribution with parameter lambda T minus S. Okay. So what we do is, I think I will skip the rest of the steps, but it is very clear from now on. We just need to sum up all the even numbers generated from this Poisson distribution. K even. Sum up all the even numbers. Well, each K follows from this Poisson distribution. So you have the this Poisson distribution is lambda T minus S to the power of K and E negative lambda T minus S and K factorial A even. And this is where, okay, this is only the even part, this part, right? And you have to get the odd part. The odd part, same thing. This is where you started to need this hint, right? This hint. It's the same thing, except that T now becomes T minus S. Okay. So basically, these two sum becomes two simple exponentials times cosine H and sine H functions. Okay. And then you further simplify because cosine H and the sine H can represent by exponentials. So okay, you just simplify and simplify and simplify. Here I will jump to the solution. You get, in the end, you get this result. Okay. This is when you assume T is bigger than S. If T is smaller than S, you get the exactly the same expression, except you have S minus T instead of T minus S. Okay. So combining two cases, this guy is basically this exponential where inside you have absolute value of T minus S. Okay, combining this t bigger than s and t less than s, these two cases. And we know that in this case, this autocovariance, right, it is equal to the autocorrelation because we have zero mean. This is a zero mean process. Yeah, this autocovariance equals to autocorrelation. But this guy only depends on t minus s. Only depends on t minus s. So this is by definition, it is a wide sense stationary process, WSS.